So this is a pretty tough question. I hope you were able to solve it. There are lots of different ways to solve this. I'll start by working out one way on the sketchpad, and then we'll see a few different ways to solve it in the Python interpreter. So I'm going to call the three inputs A, B, and C. We can call them anything we want. And since they're not meaningful numbers, might as well just use the first three letters. So one way to solve it is to have a big complicated nested if statement. So we're going to have several comparisons. First, we want to check if A is greater than B. If A is greater than B, well, A might be the biggest, but we don't know yet. We still have to check if A is greater than C. So we need two ifs. And the important thing to notice about the two ifs, the comparison A greater than C is indented inside the if A is greater than B. So this will only happen when A is greater than B. That means if A is greater than B and A is greater than C, A is the biggest, so we can return A. If it's not, well, now we've got the case where A was greater than B, A is not greater than C, so that means C is greater than or equal to A. So now we know that C is the biggest, since C is bigger or as big as A, and A is bigger than B. So now we can return C. So when this is not true, we know that C is greater than or equal to A, and we know that A is greater than B because this test evaluated to true, so we know it's correct to return C. Now we want an else that corresponds to this condition. So here, if A is greater than B, we evaluated this code. If A is not greater than B, well, that means we have B is greater than or equal to A. And in this case, we want to check whether B is greater than C. So we need another if. We're going to use if B is greater than C. Now we know that B is greater than C. B was greater than or equal to A because we went to the else here. So that means we can return B. If not, well, then we know B is greater than or equal to A, and C is greater than or equal to B, which is greater than or equal to A. So that means C is the biggest. We should return C. So here we have a definition of the biggest. It's pretty complicated. We have three different if statements. The main one that starts by comparing A and B, and then within that we compare A and C. Then we have the else, and within the else we compare B and C. Whenever we have lots of nested if expressions, and certainly we can have more than this amount, but this is already getting to be enough to be confusing, we should try to think if there's a clearer way to do this, a way to make the code smaller and simpler, easier to understand. And if it's easier to understand, that means it's also easier to write it correctly. So the easier way to write this would be to use the bigger procedure that we defined earlier in this unit. And if we remember what that was, we defined bigger like this. Bigger took two inputs. It compares them. If A is greater than B, it returns A. If not, well, then B is bigger, or at least equally big, so we can return B. So if we have bigger defined, which we already did, then we can define biggest in a much simpler way. We don't need all these ifs. All we need to do is use bigger twice. So if we remember that we have the biggest procedure, well, then we can think about biggest this way. So we've got three inputs coming into biggest, and it should produce one output, the biggest of those three. Well, we've got the bigger procedure, so we could use bigger to compare to. So if we put A and B into bigger, the output here is going to be the bigger of A and B. To know the biggest of the three, well, now we need to compare that one with C. So the inputs to this bigger procedure will be the result of bigger of A and B and the input C. And the output of that will be the biggest of the three. So this is composing two calls to bigger. We want the inputs to the first call to be A and B. We want the output of that call to be one of the inputs to the next call. So here's how we can do that in code. We can return the result directly, and the result will be the result of bigger, and this is the last bigger. When we do composition, we need to think about the function that we actually do last coming first, because that one needs the inputs of the other ones. So the input to this call to bigger, it has two inputs. It has the result of this one, which took A and B as its inputs. So that's what's here, taking in A and B, producing this output. That's one of the inputs. And then the second input to bigger is C. So that's a much shorter way to write biggest. Takes advantage of the fact that we already defined a procedure that does this for two inputs. And now we want to do the biggest for three inputs. There's actually an even easier way to do it, and that's using a built-in operator. There's a built-in operator max, and we could use max directly to implement bigger, just returning the max of A, B, and C. If we actually knew about the built-in operator max, well then we wouldn't need to define biggest at all. We could just use the built-in max. But the important thing to see here is that we can define procedures ourselves. And in fact, we've seen enough at this point that every built-in procedure in Python, you could actually define yourself. And it's even better than that, that you actually know enough at this point that you could write every possible computer program using just the things that we've seen. And this is a pretty astounding result. And I mean this in a very strong sense, that everything that could be computed mechanically by any machine can be described using a program that only uses the things that we've seen so far. All you need is procedures, simple arithmetic with the comparisons, and if statements. And this is a pretty amazing thing. This was shown by Alan Turing back in the 1930s. Alan Turing is probably the most important computer scientist. In the 1930s, he developed an abstract model of a computer, which we now know as a Turing machine. And he proved that that machine, with a very few simple operations, could simulate any other machine. I should point out that Alan Turing was doing this back in the 1930s, when there weren't computers like we think of today. In the 1930s, what someone thought a computer was a human who did calculations. And they did calculations in a mechanical way, following steps such as what you might have learned in grade school to do long division or long arithmetic. Alan Turing showed that a very simple model was enough to capture everything that a mechanical computer could do, whether it was a human computer or a modern computer that operates electronically like we think of today. Following World War II, he worked at Bletchley Park. This was the headquarters where all the British efforts to break the Nazi encryptions were done. Alan Turing led the effort there to break the Enigma code. Enigma was the most widely used cipher code by the Nazis. And Alan Turing built machines that could be used to break the Enigma code. These were sort of like computers. They would do lots and lots of calculations. The big difference between these machines and what we think of as computers is these machines weren't programmable. They were built for one very specific task, for doing a calculation that was useful for breaking Enigma encrypted messages. And it was tremendously useful that they could do that. This had a huge impact on World War II. But they weren't computers because they couldn't be programmed to do anything else. We're not going to get into the theory of Turing machines in this course, but I hope you'll take one of the later courses that we'll do. The important point to make now is that with a very few simple operations, you can simulate any other operation you want. And you've seen arithmetic, you've seen comparisons, you've seen how to define and call procedures, and you've seen how to use if to make decisions. This is enough to simulate anything else a computer could do. So with just that, you could write every possible computer program. We could end the course here, and you could, from just the things that you know now, build any computation you want. We're not going to end the course here, though. And the reason for that is, although you could, in theory, build every computation using just these very simple things that we have so far, that's not going to be the best way to build computations. That there are more powerful constructs that we can use that mean with a smaller amount of code or in a more elegant way that we can write the computations we want. We also have a lot to learn to get practice using these to define more interesting programs. But in theory, everything that you need to know to write any possible computation, you already know from just these constructs that we've seen so far.